Right, so this is the third type of applications under derivatives. Uh, First we looked into curve sketching, and second we looked into rate of change of certain quantities, and this is the most practical aspect on the derivatives that you would find in this course, right? I mean in A-levels, right? So when you go to university, you would be directed to many other applications, obviously. But in this course and this syllabus, you will be only looking at these types of applications. Right, so let me picture a scenario first. Suppose in your lifetime you would come across situations where you would have to optimize a certain problem, or you have to find the optimum solution to a certain problem, right? Suppose, for example, you wanted to go from I mean you want to go to school, right, on a rainy day. On a rainy day you want to go to school, so there are many options available. You can walk to school, which is not very practical, or you can take the bus, or you can take tuk-tuk, you can take a vehicle if you have one, right? So depending on the routes, the time it takes for you to go from home to your school will differ, right? Suppose on a rainy day there will be traffic on the road, right? So maybe the best option would be to take the train. Doesn't matter. So you might need to come up with the optimum solutions, which path you would take so that you will not be late to school, right? So that is the kind of scenario you will be looking at. Right? So in these types of scenarios, you need to come up with the optimum solution. Right. So you might come across situations where you would need an optimum solution to a problem. So I have given three examples here. So basically, I will not be doing a lot of practical applications, even though we have them as problems in your tutorials. So you can do them. I'll be looking into the past paper problems mainly, because the past paper problems mainly focus on volumetric optimization and areal optimization. So that's what we'll be focusing more on. But in the examples, I have given you certain things. For example, design a container of a certain volume with existing materials such that the cost is minimized. Suppose you are at work and your boss comes and tells you to design a container. You need to design this container. Maybe this would be a special container. Maybe this container should contain radioactive materials. If it should contain radioactive materials, then you need to you can't use polymers or steel or anything. You have to use maybe lead, right? Certain materials that will restrict the radiation. Okay, so that would be very costly. So what is the optimum design solution? For example, let me just say your container should contain a certain volume. Okay, so let's look at a cylindrical container here. For example, this is a container. You can see a cylindrical container. It has a radius and it has a height. Right circular cylinder there. Right. So I can design this container in any way I want. Suppose this wall of the container should be made with an expensive material, right? So if the surface area of the wall is high, then that means your cost is high. If the surface of the wall is low, I mean when you want to now, since it is very costly, you might think then I should lower the surface area of the wall. If you lower the surface area, this would be your container, the shape of the container, right? So if you use this type of container, it will take a lot of space into account. And who knows, maybe the top and bottom material is high, the amount of top and bottom material is high. In that case, again, it would account to the cost, the final cost of the design, right? So this is a problem you get. What would be the optimum design? What would be the radius? What will be the height? That is what I meant by the optimum design, so that the cost is lower. Right. This is one example. And then what is the dimension of a cube that can be inscribed in a sphere such that its volume meets maximum? Cubo, let's say this is okay, something like this. Right? So I said cube, so obviously a cube can be a cube is the you don't need derivatives to find this problem. I didn't think this too. Okay, right, good. Maybe let's move into the next one. What is the shortest path a man can take if he has to both swim and run? Suppose in this case, suppose you live near the shore, you have a house, there's a man, and there's an island here. There's an island, right? So here it's sea. If it is sea, then if the man has to go from A to B, the island, what can he do? He can walk from here to here, walk or run as fast as he can, and then swim through the ocean until he gets to B. This is just one path, one option. Or he can just jump right away and swim across the sea, not across the sea, swim to this point, to this island, right? This is the second option. Or he could just run up until a certain point here between these 2 points, then swim. This would be a third option. So what would be the fastest way for him to get from here to here? That can be decided using derivatives. The optimum solution can be decided. This is quite similar to the example I told you guys at the beginning, where you want to go from home to school amid a raining day, right, a raining season. Right, so these types of, would be mostly looking into these types of design problems where you need to optimize the design of a certain shape. Right. So we'll look into some examples, maybe 1 or 2 examples in this video. We will look into more examples during the discussion, and then we will get to know what we actually doing here, what is our objective. Okay. Right, so I brought a string here. I couldn't find one wire, right? This is what I had that resembles a wire, right, closest to wire. Now this is an example, a thin wire of length 2L. You will see why I took it as 2L instead of L, right, in a moment, is bent into a rectangular shape. Now this is a problem. We have a thin wire and you are asked to bend it into a rectangular shape. So when you bend it, then you get a rectangular shape like this. You have to design this, right? So I didn't say what the length and the width of the rectangle is. The first one tells you to bend it into a rectangular shape. The next would be the optimization problem. To determine the length and width of the rectangle. So you have to determine the length and width of the rectangle such that its area is maximized. Now when you have a length, now I have connected this, so I can make rectangles of any shapes like this. You can see when the width is small, the length gets bigger, and if I increase the width, the length gets smaller and smaller, right? You can see at each case, at each design, the area will change. The area of the shape will change according to the design, right? So here area, you can see area is what is covered by this line right here, So you can see area. So what would be the optimum design such that this area is maximized? So you would have uh, you have an idea about it already, but we will show this using mathematics. So what we can do is we can do just a trial and error method, not trial and error, just do trials. For example, this would be our rectangle. The rectangle. Keep in mind that you are given a thin wire that you can bend, and the length of the wire is 2L. So in these types of problems, there will be a certain condition. A condition has to be met, or limitations, right? Restrictions. These are given. A restriction or limitation is given. So what is the limitation? You are given a thin wire of length 2L. So whatever the shape you get, the perimeter must be equal to 2L, because the length of the wire is 2L, right? So you are restricted in a certain way. Otherwise you can make bigger rectangles so that the area is maximized. Determine the length. Now we have to design. Now here's the thing. This is a rectangle, so I'm going to put a variable because I don't know what the values are. For example, let's say let's take 2L. Suppose 2L is 100. Then we can take say 30, 30, 20, 20. So we get 40 and 60, that is 100. Okay. So what is the area in this case? Area is 600. Oh, I can do this shape. For example, would be 10, 10. Then this is 40, 40. What happens to the area in this case? In this case, the area is 400. So you can see area here is 600, area here is 400. So out of these options, this should be the winner out of these options. But there are many other options. For example, this could be 35, 35, 70 and 15, 15. So area in this case would be 35 into 15. So I'm not gonna find that out. You have to find it on your own. So we don't know what it actually is. Or it could be 25, 25, 25, 25. Okay. So in each cases, area will change. There will be a corresponding area. If you are doing this practically, then what you have to do is we have to come up with each design and the dimension of the design. Then based on the design, you can find the area. Then what you can do is you can just find the determine the area by taking many designs, right? Many designs, and figure out which one would be the maximum, which one give you the maximum area. So this is impractical, not practical, because there are infinite number of possibilities available. Out of infinite possibilities, you can't test all the infinite possibilities. So this is impossible task. It's not possible. So there is a mathematical way. What can we do here is that the first thing you do is to come up with a design, just a basic model. Just model this. So if this is our rectangle, suppose this is x. This is x. If this is x, then this should be x as well. X is the length. Then the width. Let's say this is y and this should be y. So in this case, our area is x into y. Our area is x into y. Now notice here that area depends on two variables, x and y. So in these kinds of problems, you would come across these kinds of expressions where you would think that this is a function of two different variables, but actually this is just a function of a single variable. The reason is that due to this limitation, length to width. So in almost all the problem you get, you will be the dimensions will have a dependencies between them. So even if you think that this is you have two variables here, this is actually just one variable. Now in that case you have to get rid of one of these variables. So you know that 2x plus 2y is equal to 12. This is why I use 12 here. So 2 cancels out. So you can replace any one variable with the other L minus x. So this is called the restriction. Right? This is the restrictions. In certain cases, volume could be restricted. So they would say, I need to design a container of 1000 liters. So 1000 liter would be the restriction in that case. So you should be intelligent enough to figure out the restrictions. So when you figure out the restrictions, you should be able to replace one variable with the other. Now based on this restriction, I can write A as x into L minus x. X into L minus x. Now you can see we found area as a function of x. So in this case, we found area is equal to a function of x is length. Now based on this, what you can do, you can just draw a graph, right? Draw a graph. You know how to draw a graph. If you didn't know anything about derivatives, then you can use the plotting method you use in O levels. So what you can do, you can just get a table out of this and plot the point on a graph paper and get a curve, right? Function of length. Now what is this? This is actually so you can see this is xl minus x squared, xl minus x squared. This is a maxima function. So the maxima function. So what are the roots? Root would be at x equals 0 and x equal n. So it would be a function like this, right? So notice here I'm using a discontinuous line because x is a length and x cannot be negative. X cannot be negative. That's why I'm using a discontinuous line here. I'm using discontinuous line just for the illustration purposes. Here also x cannot be greater than L. X cannot be greater than L. If it is greater than L, you don't get a rectangle. So that's why I plotted this line like this using dash lines. Okay. Now you can see when you draw this function, in a plane, Cartesian plane, where this axis is the area, x axis is the length. So you don't need these parts because you don't have any negative areas here and no negative lengths. So you have to make okay. So there will be a restriction again. So let me write it, x is less than L C. So this will be given in the problems. Now what is the maximum area? Suppose you selected a design like this, your x is here, then the corresponding area would be this. You select x somewhere here, the corresponding area would be this. So what would be the maximum area? The maximum area would be at the maximum point of this graph, which is this, right? This would be area max. So what is this point? Maximum area. It's actually, so based on this symmetry, you know that this point is actually L by 2. If this point is L by 2, then maximum area would be L by 2, then L by 2, so L by 2, L squared by 4, L squared by 4. If x is L by 2, then y is also L by 2. If x is L by 2, that implies y would also be L by 2. So what would be our optimum design? Our optimum design such that the area is maximized would be a square. A square of side length L by 2. This is why squares are very important, because a square will give you the maximum area for that given for a given perimeter, right? For a certain perimeter, square will give you the maximum area, not a rectangle, square. That's why squares are very important. Now you can see this is how you should do it if you don't know anything about derivative. Now you can see that this is a maximum point. So what happens at maximum point? How do you find the maximum points? So when you sketch graphs, you know you found these turning points by this. dA by dx is 0 at this point. So if you make dA by dx equal to 0, this would give you the x coordinates at the turning points. Right, so this is what we're going to do. We're going to get a function. So if you want to optimize a certain problem, you need to write that problem as a function of a variable. Then you're going to derive that problem with respect to the given variable, right? Then you can equate that to 0 to find the turning points, maximum points or minimum points. So then you will get the answer, right? So this is the easiest method. You don't have to go through all of these steps. You just have to get the function, then take the derivative and equate that to 0 to obtain the maximum and minimum point. Now dA by the derivative would be 0 at maximum points, minimum points, and the certain types of points of inflection. So you have to make sure, you have to show that the given point is also maximum or minimum or inflection. So for that you can use the first derivative test. It will be very easy, it won't take much time, it's very easy to show that as well. So you can see that when the problem is simple like this, then you can draw a function, but when the problem is more complicated than this, then you should not go into sketching the function and then determining the optimum points. Just have to use the derivatives, right? Skills of the derivative would come in handy at such point. So let me do the same thing by using the derivative. This is the old method. Now we know the derivative, so let's use that. Still you have to get this function, right? Area, you have to maximize the area. So area, write area, that quantity to be maximized as a function of the given variable or the variable that changes. Then to find optimum point, all you do is derive this dA by dx. Derive this. When you derive it, you get here L minus 2x, right? L minus 2x. Then equate this to 0. Equate that to 0. So when you equate a first derivative to 0, that will give you the x coordinates or the values of the independent variable where the function takes a turn, right? So this would give you us, if you equate this to 0, our x would be L by 2. You can see you get the same answer as before, L by 2. Therefore, the design would be, the perfect design would be L by 2, L by 2. And the maximum area is L squared by 4. Maximum area is L squared by 4. Now, you cannot write this because dA by dx equal to 0 at maximum, minimum and also inflection point. So you have to corroborate your answer by doing the first derivative test. before writing this, you have to do the first derivative test. You already know how to do the first derivative test, so I'm not gonna go through that. So let's look at another problem. Right, so this is another problem. Same thing. In the previous one, I bent my thin wire into a rectangular shape. Now in this example, they are asking me to bend it to a sector of a circle. So what is a sector? You know that when you have a circle and this one here represent a sector of a circle. So this one here, this part is called an arc. It is the arc of a sector, and this complete part is called a sector, right? So they are asking me to build a sector of a circle using a thin wire. So I have to shape it into a sector, and the radius is r. Radius of the sector is r. So you have to do a model, right? Just sketch a model. So let me speak. You have this sector, r is the radius, and it will have an angle theta. So theta here is in radian. You learned this in trigonometry. So what is the length of the perimeter of the sector? Not the perimeter. The arc length of the sector is given by r into theta. This is r theta. So this is the wire. Now this is the wire, right? So y is bent into a sector. Now what is the restriction? The restriction is r plus r plus this length r theta is equal to L. Sorry, 2L. This is equal to 2L. Right. So here I have 2r. Then if I take r outside, then I get 2 plus theta is equal to 2L. This is equal to 2L. Right. Now you can see we have two variables here, theta and r. Right. The moment you see this problem, you might wonder there are two variables, but actually one variable is it depends on the other variable. In that case, due to this limitation here, the restriction. So you can see that theta can be replaced by r in this case if you want. So in that case, theta would be 2L over r minus 2. 2L over r minus 2. Okay, this is our limitation or restriction. Now, first of all, you have to find the area of the sector in terms of r, right? So theta is something that you put into. So you have to find the area in terms of r. So what is the area of a sector? Area of the sector is half into r squared into theta. R squared into theta. Therefore, A is half into r squared is given because we have to find it in terms of r. Then theta can be replaced by this. So let me take 2 outside, then I get L by r minus 1. So if I cut this off, I get r squared L over r minus 1. This is how so I have determined the area of the sector in terms of r. L is there because L is given in the problem. That's fine. Then hence find the radius and the angle of it such that its area is maximized. So I can change this r, right? I can do a sector like this, right? Sorry, like this. I don't know. So if r is bigger, then your sector would look like this in this case. So which one will give you the maximum area? This is impractical. You can't do this by trial and error method. So what you can do here is that you can derive when the function is obtained. You have to derive this dA by dr. dA by dr, because when you change r, this would be the variable. When you change r, it will change the area accordingly. Right. So I suggest you to expand this out. Otherwise, you would have to use the product rule here. See, when you expand it, you get r into L minus r square. So this would be easier to differentiate. So when you differentiate this with respect to r, you get L minus 2r. L minus 2r. Now, for optimum values, for optimum r, you have to set dr by dA by dr equals 0. This implies r would be L by 2. R would be L by 2. So we found a value for r such that the function has an optimum point. It could be a maximum or minimum. We don't know yet. So that's why they are asking us to justify my answer. Justify my answer. Right. So we took this one. Let's justify our answer. How do we justify it? Using the first derivative test. Here you can see dA by dr. So I use the number line. And we draw the number line, then L by 2, L by 2. So if we are less than L by 2, if it is less than L by 2, suppose R is L by 4, less than L by 2 means let's take L by 4. If you put L by 4, then this would be L minus L by 2. It would be a positive value, right? If you take let's say a value which is greater than L by 2, let's say L, if you put L, then this would be 2L, so L minus 2 will give you minus L, then you have a negative value. So our grade, the shape of the gradient dA by dr would be like this. Okay, I hope you see. Now you can see our dA to the left side of L by 2 it's positive, to the right side it is negative, in the middle it is 0, so that's why it's horizontal. This tells us it is a maximum. Therefore, A is a maximum at R equals L by 2. At R equals L by 2. Now this is the this should be the radius of the circle such that the area of the sector is maximized. They also ask us to find the angle. So to find the angle, you can just use the relationship here given when this is L by 2, 4 minus 2 is just 2. This is 2 radians, rad, 2 radians. Okay, so L by 2, 2 goes to the top, yes, okay, 2 radians. Right, I think now we have a pretty good idea about this optimization problem, so we'll look into more examples during the class. Thank you.